Всем привет! Меня зовут Никита Соболев, и это «Лучший курс по питону». Сегодня мы продолжаем говорить про float, и для того, чтобы рассказать про многие интересные детали из истории, а также из будущего этого стандарта и этой имплементации, я пригласил в гости Майкла Овертона. Он один из членов рабочей группы IEEE и, соответственно, автор книжки по тому, как устроен float, а также профессор университета в Нью-Йорке, который в том числе преподает устройство float. Так что это максимально компетентный человек для того, чтобы поговорить с ним об этом замечательной технологии. Мы будем говорить с Майклом на английском, но я подготовил для вас английские и русские субтитры. Соответственно, если вам проще смотреть, можно смотреть. Если вам хочется и смотреть, и читать, для этого есть все необходимые материалы. Поэтому приятного просмотра. Давайте напишем Майклу что-нибудь приятное, потому что он действительно очень помог подготовке этого видео. Спасибо. Michael, welcome to my channel. Today we are going to speak about float and double and how these two major abstractions and implementations affect other programmers' lives. So please introduce yourself.
Oh, thank you. Well, it's very nice to be here. Thank you for inviting me, Nikita. My name is Michael Overton. I'm a professor of computer science and math at NYU, New York University in New York. Well, I've been there my whole career. And it's not my primary interest, but one of my interests has been floating point arithmetic for a long time, mainly because I got into that because I was teaching numerical computing in the computer science department. And I was really interested in explaining to the students much more about how the computing worked instead of, the typical thing in a numerical analysis class in a math department is you spend about 15 minutes talking about that, and then you talk about all these mathematical methods. But actually, the details of the computing are very interesting, especially to computer science students. So I ended up writing notes, and then that turned into a small book that I wrote that was published for SIAM, Society for Industrial and Applied Math, in 2001. And then, well, I left that book. I mean, I used the book over many years, but didn't really look back at it much the last 20 years until recently. I had the opportunity to write a second edition because so much has changed since 2001. Yeah, that you won't know yet. So much has changed since 2001. The basic principles are the same, but technology, of course, has totally changed. And so I'm actually pretty close to finishing the second edition, which will be published by SIAM, well, presumably in 2025.
Oh, great news. Can you please explain a little bit for the audience, what did exactly change?
Maybe it would be better to first explain what happened in 1985 with the original floating point standards.
Yeah, sure.
Okay? So if we go back further in history, and then we'll come back to the present later. If you go all the way back, floating point was actually first developed by Konrad Zuse during World War II in Germany. He actually built a binary floating point arithmetic computer. It wasn't electronic, though. It was electromechanical. And then later, the first electronic computers were developed. There were a lot of people, of course, were involved in this whole process post-war, particularly von Neumann and Turing. And then various companies, of course, started building electronic computers and marketing them, particularly IBM. And there were all these different ways of doing computer arithmetic. And it was very confusing because you might run a program, say Fortran in those days, the Fortran program on one computer, an IBM computer, and you might get quite different results from if you ran it on another computer, because the way the arithmetic was implemented on the computer was quite different. So there were a lot of people who were concerned about this, and the floating point standard was developed it was finally published in 1985 after about 5 years of work. This was back actually soon after I was a grad student. I wasn't involved in that, but some of my colleagues and close friends were, and particularly Professor Valvel Kahan of Berkeley, who led the whole process. He was also involved in designing the floating point chip for the at that time new Intel 8087, which was the floating point chip. It was actually a floating point coprocessor that worked along with the 8088 that they were developing. And Kahan was heavily involved in the design of that, and a lot of the same ideas were adopted by the standard, which was published in 1985 by IEEE and then adopted internationally as well. So what happened was that the standard had an enormous impact because at the time, there were various so-called mainframe computers, VAX, DEC VAX, HP, IBM, I already mentioned, various others. Many of those names have gone now. They were all doing their own thing, and none of them really wanted to change what they were doing. But then what happened was that the personal computers took off like crazy, particularly with the Intel chips, which were adopted by IBM and the IBM PC. And then all the other manufacturers of microprocessor chips that were used in PCs, particularly Motorola, they all adopted the same standard with the same standard arithmetic. And eventually the mainframes all faded away, like the big IBM machines, which totally dominated computing in the 60s and 70s. People weren't reusing them so much anymore. People were much more using the new Intel chips, and that continued to develop over the years. So the standard was hugely successful. The industry really adopted the changes. But in terms of what's happened since, well, the main principles of the standard, which I can explain more about later, are still pretty much widely adopted. But those are the 32-bit and the 64-bit floating point words, the single and double formats. And what's happened most recently is that with the massive amount of computing required by machine learning, the various companies manufacturing the chips used by machine learning, including Google and NVIDIA particularly, they've started to use these shorter formats, 16-bit and even 8-bit, and now even 4-bit floating point format, which is completely, well,
inaccurate.
It's a sea change, very inaccurate. Yes, scary, one might say. We could talk more about that later, but yeah, back to you.
So yeah, thanks a lot for this very brief and deep introduction to the floating point history. And you mentioned that basically IEEE standard had a huge impact on the industry. And why exactly this standard won the race among many others?
Well, it was the only standard, actually. What happened was that there were all these different manufacturers doing their own thing, and the standard said, no, let's all do this. And there wasn't any competing standard. And as I said, because of the phenomenal growth of the PC industry and the chips that were used, excuse me, in that industry, particularly the Intel chips and the Motorola chips, they just all adopted the standard. It was just, they all agreed, hey, this is a good thing. Then people's programs will run as expected on different machines. And so there wasn't actually a competing standard. What there was there was a lot of debate in the committee, which included academic computer scientists led by Kahan, and also a lot of industry people from all the big names in industry at the time, IBM, HP, and so forth, DEC. And they all argued, of course. They didn't all agree on what should be done at first. But Kahan's viewpoint was, well, very forceful, but also very well grounded in sort of theory and common sense. And also another thing that helped a lot, I think, is that Kahan, he's a professor of computer science and mathematics, I think, both at Berkeley. But also he came from Toronto, where he had actually a lot of training in EE, electrical engineering as well. So he knew what he was talking about when he talked about, hardware. He wasn't some guy who didn't know any of that stuff.
I I
So
think that
in brief, they listen to him.
yeah. I think that the standard has a lot of great stuff inside. But I want to also highlight some problems that might be hidden in this standard. Do you have any existing examples? For example, in your book, you mentioned that gradual underflow is the most controversial part of the standard.
It was, but one thing that's changed is that it's no longer controversial. It's pretty much been adopted in hardware. What happened was that in order to, well, maybe we should explain first for our listeners what gradual underflow is.
Yeah, sure.
So in a floating point format, you only have, let's say, 32 bits, and let's explain first how before we get into underflow, let's explain how these 32 bits are used. So there's one bit that's needed for the sign of the number, plus or minus. So now you're down to 31. Now the format they agreed to adopt for various reasons used the next 8 bits to represent the exponent in the floating point. So floating point is a system sometimes compared with scientific notation where you have, let's say, well, the simplest example, let's say, let's take the number 16. Okay, 16 is 2 to the power 4. Well, in binary, because we always use binary in floating point, that's another story. There is actually decimal floating point too, that is used in business. But scientifically, in scientific applications, by far the majority of applications, it's binary floating point that's used. And so the number 16 in binary is 1.0000, et cetera, as many zeros as you want, times 2 to the power 4, right? 16. 16 is 2 times 2 times 2 times 2, 4, 16. So the 4 is stored in the exponent field of the 32-bit word that you have up to 8 bits, so you can go up to about an exponent of something like 127, because you have to allow for negative exponents as well. And then the remaining 23 bits in the word, right, because there are 32, but we've used 1 for the sign, 8 for the exponent, that's for the so-called significand. So in the case of 16, because it's the exact power of 2, it's just 1.000 and then a bunch of zeros. But a more complicated number like pi, of course, or even something like, say, almost any number really, is not going to be 1.000, but it's going to be, it's going to have a bunch of ones and zeros in the expansion of. So you have 23 bits for this significand, plus another bit that's so-called hidden, but let's leave that aside for the moment. And then you've got these 8 bits for the exponent. And the exponent, as I said, it ranges from basically from, it's something like minus 127 to plus 127. There's a couple of special exponents to represent special numbers like 0 and infinity, which is another interesting number. But the business of the gradual underflow is what happens when a number gets down to 2 to the minus 126, I think it is. Below that, you might say, well, look, we can't store a number that's smaller than that, so we're going to have to drop it down to 0. That would be not gradual underflow, but abrupt underflow. But gradual underflow says, well, no, actually, by being a bit more clever, we can actually store 2 to the minus 127, 2 to the minus 128, all the way down to, it's actually 2 to the minus 149 in so-called single precision, the 32-bit format. And that's what gradual underflow is. Now, as I said, it was controversial because implementing arithmetic with numbers that might be so-called subnormal, that means they've dropped below that underflow threshold down into the subnormal range using gradual underflow, having arithmetic that works with those kinds of numbers as well as the ordinary floating point numbers, the normalized ones. Well, it's more expensive, more complicated, and many of the manufacturers just didn't want to do it. DEC in particular was quite opposed to it, but Intel was highly in favor, and because of Kahan's influence probably. And but eventually everybody realized, okay, well, they were allowed to do it in software to conform with the standard, but that was a problem because then the computations would really slow down. So eventually, pretty much everyone adopted the hardware gradual underflow. So that's actually not controversial anymore, but it was back then.
Mhm.
So that's one of the things that's changed for the better.
Maybe there are some other examples.
Well, the biggest one right now is this short format thing for machine learning, but
Can you tell a little bit more about that, please?
sure. So, so the standard defines several floating point formats. 32-bit format, which is a so-called single precision. In C, that would be called float. The 64-bit double format, double precision. In C, that would be called double. I think in Python, it's called float, right? This is what you're primarily interested in. Because Python, at least the original Python anyway, works just with the double precision 64-bit floating point numbers, as I understand. Please correct me if I'm wrong.
That's correct.
Yeah. Okay, so then what about longer? What about shorter formats? Well, in the 1985 standard, they only introduced single and double, and they said to be conformant with the standard, you have to implement single, and you can implement double too if you want. And they recommended an extended format, but that's not so interesting. So the standard is supposed to be revised every 10 years, because if it isn't, it expires. That's an IEEE rule. So that means it should have been revised in 2005. Actually, the revision finally appeared in 2008 after a lot of discussion. There were quite a lot of changes in 2008. So they introduced 128-bit format, which is sometimes called quadruple precision, right? You've got single, double, quadruple, 32, 64, 128. And they also introduced half precision, which is 16-bit, but that's getting kind of short because you still need 1 bit for the sign. Now you have, I think in the IEEE half precision, you have 5 bits for the exponent, which means the exponent can only go up to 2 to the 16, right? From 2 to the minus 16 to 2 to the plus 16, roughly. And then, okay, so that leaves, so I think that leaves 10 bits for the significand, plus 1 bit that's so-called hidden, which is in every number except 0. Okay, so a 16-bit format was introduced. So that's called half precision usually, or the names were also changed. So in 2008, instead of single and double, they started calling it binary 32 and binary 64. Often that's abbreviated to FP32 or FP64. And then binary 128 and binary 16, or BF16, FP16. And then in 2019, there was another revision, again, slightly late, 1 year late. But though that wasn't a major revision, it introduced a few new things and fixed a couple of bugs, but it wasn't super major. But meanwhile, there was a big change between 2008 and 2016, and that's that machine learning took off. And what happened is it was Google first that said, okay, well, it wasn't only Google. A bunch of people working in machine learning were saying, hey, let's use 16-bit format, because you use, when you're saying multiplying two 16-bit numbers, it's much it's a process that requires much less power than multiplying 32-bit numbers. And so you save power and you save space by having shorter formats. Now, that wasn't so much of an issue before machine learning came along, but what's happened with machine learning is it's just enormous amounts of computation involved. And the reason the machine learning has suddenly been so successful is because that's now possible with the technology. It used to be that you couldn't do these kinds of massive computations. It was just much too expensive. But with computers becoming faster and faster and cheaper, now you can. And the whole idea of neural nets, which was promoted by Jan LeCun and others back even before the turn of the century, I think. He was sort of speaking, he was sort of not quite alone in the wilderness, but people weren't convinced that neural nets could ever work. And then by about 2010 or so, it became very clear they were amazingly effective. And by 2015 or 16, companies like Google, who were developing their TPU, tensor processing unit, realized that, okay, if we use 16-bit, that's going to be much faster and cheaper. But in fact, let's introduce a new format, they said, because they didn't like binary 16 because the exponent range is so small from 2 to the minus 16 to 2 to the 16. So what they introduced was something that they called B float 16. B stands for brain, Google Brain. And in that format, you have 1 bit for the sign still, but now you have 8 bits for the exponent, which is the same as with IEEE single precision. And then, okay, so that uses up 9 of your 16 bits. And so what have you got left? You've got 7 left now. And plus 1 hidden bit, which is not even enough to represent more than 2 decimal digits of accuracy. That might not be so obvious, but we could talk about that later if that's of interest. But so people were a little shocked that there's so little accuracy in the numbers, but they said, look, hey, this is machine learning. We're doing massive amounts of it, and there's tons of redundancy, and we don't need high accuracy. And you can't argue with the fact that machine learning has been enormously successful, so it apparently works. You wouldn't want to be doing that for scientific problems that require highly accurate computations. But in machine learning, it seems that's not necessary. So they introduced bfloat 16. They built their own chips. They were not exactly secretive about it. They did publish this, and then other manufacturers started following the same format, including NVIDIA and Intel, which I guess is the 2 biggest players making chips at this point. Well, maybe 1 or 2 others, but anyway, those are certainly 2 very major ones. So that's fine. And then people say, well, look, if 16 bits, why not 8 bits? So a bunch of researchers started using 8 bits, first just simulating it because they didn't have 8-bit hardware. But then again, the manufacturers started building the 8-bit hardware. So both Intel and NVIDIA announced 8-bit floating point chips. Well, that's getting really short. And now the latest thing is just a few months ago, I think it was in April or so, NVIDIA announced that they're making 4-bit floating point, which is kind of shocking. I mean, that's 1 bit.
I don't know how to even imagine their binary layout. So the first bit is obviously for sign, then 2 bits, I guess, is for exponent, and 1 bit for mantissa.
Plus, yeah, mantissa is another word for significant.
Oh, so yeah.
That's fine, just for our audience. Yeah, that's right. Plus the 1 hidden bit, which gives you 2 bits for the significant. I'm actually not sure if it's that. That's probably right, or maybe it's 1 less bit for the exponent. I'm not sure. I didn't look it up yet. I'm planning to do that very soon. Anyway, where's the limit?
Yeah, that's quite interesting.
Yeah.
You've also mentioned that hidden bits quite a lot. So can you please explain what hidden bit is?
But every number, every number except for 0 has a leading 1, right? Because you can always the whole point of floating point is you normalize, you shift the binary point so that it floats to the position. That's why it's called floating point. It floats to the position where the 1 is in front before the binary point, and then 0, 0, 0. So, well, the thing is, all numbers, whether it's pi or the square root of 2 or 1/10, 1/10 is an interesting one. Let's do that one. 1/10 is 1.100110011001100 ... times 2 to the -4, if I'm remembering correctly.
I have to use a calculator for that.
Well, I know that one by heart. That's 1/10, as it turns out. Okay.
Roughly 1/10, yeah.
Yeah, exactly. If you go on forever. But again, you see, it starts with a one. Well, of course, it starts with a one because I floated the binary point so that there would be a one in the front, right? I didn't put 0.0001100. I could have done, but the whole point of floating point is you want to float that binary point to get the one in front, and then you have times a power. But that one in front, why do we need to store it? We know it's a one. So that's the hidden bit. Now, before the standard, actually it was VAX who first started doing this, the DEC VAX. But before the DEC VAX, people did store it. And the reason is they needed a way to write zero. And zero is 0.000. You can't float the binary point for zero to get a one in front. There is no one. It's all zeros. But you see, you can represent zero instead through a special exponent. So going back again to the 32-bit format, I said the numbers, the exponents are something like -126 to +127, but that leaves a couple of numbers free. And the number which corresponds to like -127 corresponds to the zero number, and at the other end of the range, the number, the exponent 128, I think it is, or maybe it's 127, corresponds to infinity. Because in IEEE arithmetic, 1 divided by 0 is infinity.
Yeah. But this is a very interesting part. Some languages treat this as infinity, but some languages do raise an exception. For example, CPython does that. It raises zero division exception for this case. So how do you feel about this little misinterpretation of the standard?
Well, that's a very good question. I don't think that is a misinterpretation. The point is that the number becomes infinity, but according to the standard, an exception, when you divide by 0, that's an exception. This is a divide by 0 exception. And what's happening in CPython then is that CPython is trapping the exception and saying, okay, stop. And the exception is thrown by the chip. So there are various exceptions in floating point. So one of them is division by 0. Another one is overflow, where you make the number so big that it no longer fits. Another one is underflow, where you make it so small that it no longer fits, even after running through all. Actually, the underflow flag is tremendously complicated because it's set, I think, even when you go into the gradual underflow range. You'd have to look at my book, especially the second edition, to get all this clear. But
we'll
anyway,
put a link into the description.
Yeah, I don't have the second edition ready yet, but I will send you a copy as soon as it's ready.
Oh, thank you.
Yeah.
Awesome.
Yeah. But it will be published by Siam, hopefully in 2025. I'm getting pretty close. Yeah, so there's 5 exceptions: divide by 0, overflow, underflow. Another interesting one is invalid operation. So 0 over 0 is an invalid operation and generates a nan, which is not a number, which is another special pattern used with the in the floating point, using the maximum possible exponent. So again, probably CPython would trap that and stop, I guess, right? If
Yeah,
you don't
yeah.
But isn't there a way to set the compiler so that it runs with infinities and nans, or not?
I don't think so. There might be some hidden undocumented flag, something like that, but I don't think there is a documented way to do that.
I'm surprised about that, because there certainly is in C. And in the C stats, it took C and also Fortran a long time to catch up with the standard, even though C had a major revision in 1999, which was long after the standard was published, 14 years after. It didn't even mention it really, or it may have mentioned it, but it didn't do anything much with it. But in, no, I'm sorry, I'm getting that wrong. That was 1989. In 1999, they finally did catch up with the standard, and they made a lot of changes. The big expert on floating point of C is Nelson Beebe, actually. So in C, the normal default behavior is that you do generate infinities and nans. And this allows you to do something like there's this one example I like is the parallel resistance formula. So if you have two resistors in parallel, and so this is something goes back to high school.
You have this example in your book.
Yes, exactly. So there's the example. And so the parallel resistance formula is where you have two resistors hooked up in parallel in a circuit. And one of the resistors has resistance R1 and the other one R2. And that's the formula for the total resistor. So if they're the same, if R1 and R2 are both 1, then you get 1 over 2, right? So the result is a half, because half the current goes one way and half the current goes the other way. So that makes sense. But what if R1 is very small? Well, then you see most of the current goes through the resistor R1, and then the total resistance is 1 over R1 plus a little bit more, which is only a little bit less than R1, because most of the current goes through R1 when R1 is much less than R2. But what if R1 is 0? Well, if you plug R1 equals 0 into that formula and you don't allow infinities, then it doesn't work. But if you do allow infinities, you get 1 over R1 is infinity. 1 over R2 is, say, 1. 1 plus infinity is infinity. And then 1 over infinity is 0. So all the current goes through R1. There's no resistance in the circuit. So it makes valid scientific sense. Now, of course, most people are not computing with parallel circuits, but there's a lot of examples like this. And it's actually a very useful thing to have. So I'm pretty surprised if CPython doesn't allow that. Pretty much all the other languages I know do. MATLAB certainly. And,
I will have to double check that right now, because
yeah.
I now begin to doubt myself.
It may
Michael,
be that it's a setting you have to choose.
I've double checked this right now, so you cannot configure CPython not to raise this error. I guess the main motivation for that is because Python tries to be very user-friendly, and I can see a lot of use cases where infinity is not very user-friendly. Do you agree with that?
I think it's something that's, yeah, a lot of people have different opinions about it. It's, yeah, certainly infinity makes sense, but of course nans really don't. Nans are basically telling you, look, it doesn't make any sense. What people sometimes use nans for is initializing data, and then the data that's supposed to be then set to other values. And if something is still a nan at the end, something's wrong.
It's called signaling nan, as far as I know. Yeah.
There's two kinds of nans. There's signaling nans and quiet nans. And the difference is kind of complicated. Yeah. So I can tell you a bit if you're interested about what's going on in with the yeah. Let's see. Did we finish about the exception? Maybe I'll just reiterate about the exceptions. Yeah. So there's 5 exceptions. There's division by 0, overflow, underflow, invalid operation, which is something like 0 over 0, or the square root of -1 would be another invalid operation, unless you're in some kind of mode like MATLAB where you allow complex numbers. And then also another example of an invalid operation would be infinity minus infinity, because it doesn't make sense, which one is bigger. Infinity plus infinity is infinity. The fifth exception is when the result of a computation is not an exact floating point number. But that's kind of a misnomer to call that an exception, because actually that's what happens almost all the time. But anyway, it's still called an exception for some reason. And so there's a flag for that too. But that's another big thing that's changed, is that this whole business with flags. You see, it used to be that setting flags was a good thing to do. And then, the compiler the runtime process can check the flags and so forth. But now with all these much more complicated things like multi-threading and so on, flags can actually kind of get in the way. And so they're not, this is really beyond my expertise. I'm not a computer designer. But from what I've heard, there's not so much enthusiasm for setting and checking these exception flags anymore. But that may not be the case with CPython. It sounds like maybe it's not. So what's going on with the floating point? Well, with the 8-bit floating point, what's happened is that there's now a new IEEE committee called Committee P3109. The original IEEE committee, the floating point committee, was called IEEE P754. And you hear all the time about 754 arithmetic, IEEE 754. Anybody knows much about floating point has heard about 754. It just means the IEEE floating point standard. So that was 1985. I guess they were numbering them sequentially. So now we're up to 3,109 for these working groups of the IEEE. And but not very many of them, of course, have to do with floating point. IEEE is a huge organization. So 3109 is a committee that was set up to make recommendations for standardizing 8-bit floating point. And so I was contacting these people to find out more about it. And they said, well, look, why don't you just join the committee? And so I did. And actually, it's been extremely interesting.
Oh, I didn't know that.
Yeah. So no, you wouldn't, because that fact hasn't been published. But the 3109 committee has now published an interim report, which I was involved in a tiny way, along with all the other committee members. The leaders of the committee, there are several leaders, the secretary, well, but let's not get into the personalities. But anyway, there's lots of very competent people, of course. They're mostly machine learning experts, but there's also floating point experts. Well, of course, some of them are experts on both. I don't know much about machine learning, but so I'm in there from the floating point side. But there's also a bunch of hardware people, like people from Intel, and actually, I don't know if there's anybody from NVIDIA on the committee, but definitely there is from Intel and other companies. And so the P3109 committee has published an interim report. Now, it's not clear how much impact the 3109 recommendations are going to have compared with the 754 recommendations, because the industry is moving very fast and the companies are not waiting around to see what the committee does. Maybe it will become standardized following the committee recommendations. I guess that's what we hope. The recommendations right now are that with only 8 bits, you have to be a little more, you have to be very thoughtful about what you're going to use them for. Now, going back to the 32-bit and 64-bit IEEE, the original single and double floating point formats, which are ones that are mostly used. So those ones, as I said, there's special representations for infinity, also minus infinity, 0, but also minus 0, which is another complication that was also kind of controversial, because if you're going to have 1 over infinity is 0, well, then shouldn't 1 over minus infinity be minus 0? And anyway, if you're going to represent 0, you've got to do something with a sign bit. So why should it always be the positive sign bit? Why not negative? So there's actually 2 representations for 0 in the original IEEE format. So there's 0 and there's minus 0. But then this leads to some very interesting unexpected behaviors, because is 0 equal to minus 0 if you check that in a programming language like Python?
Yeah, it is.
It is. That's right. Sorry, this wasn't meant to be an exam question, but you're exactly right. But on the other hand, is infinity equal to minus infinity? Well, absolutely not. They're very different. So that means that A can be equal to B, but 1 over A not equal to 1 over B, where A and B are 0 and minus 0. So that's kind of disconcerting, to say the least. But, well, really, the choice of having minus infinity really leads one to having -0. And if you're going to have 1/0 is infinity, then you really you're kind of stuck with the idea of if you're going to have two infinities, you're going to need to have two zeros also. Well, P3109 discussed all this. This was actually before I joined the committee. And the decision they made was, or we made, I suppose, although I wasn't involved at the beginning, for better or for worse, there's only going to be 1 0, no -0 in the recommendation. Also, there's multiple nans in IEEE. As you pointed out, there's signaling nans and quiet nans. And it's actually a lot of different nans because what you can do is you have all these extra bits you're not using anyway from the significand field corresponding to the special exponent field for the nan. And so you might as well use them to code the origin of the nan. So there's a lot of different nans in IEEE. And you can't test whether one is equal to another. A nan is never equal to anything, even to itself. But they can still be, the bit patterns can still be examined. Okay, well, 3109 in the 8-bit format decided no, we don't want so many nans. We can't afford the space. So there's only going to be one nan also. And they're using the bit pattern that normally would be used for -0 to represent nan. So that means you've got 1 0, one nan. Now, what about the infinity?
Two infinities.
Two infinities, but 1/0 is not infinity because if it was, and then if it was, and then you took 1/infinity, that would give you 0, but 1/-infinity would also give you 0, and then you took 1/that, and you'd get +infinity. That really leads to confusion. So the recommendation right now, I don't think this has been published yet in the interim report, but probably what is going to be recommended is that 1/0 is nan, not infinity.
Oh.
So that's the current proposal. It hasn't been voted on yet, I don't think. So this is all very
what's your opinion on that? Because from the mathematical standpoint, I guess they both do not and do make sense at the same time.
Well, I think my opinion is the committee is right that if you're not going to have -0 and you are going to have ±infinity, then you should not say that 1/0 is +infinity because it's too confusing. And just to reiterate what I just said a moment ago, because I went very fast. If you have -infinity, 1/-infinity would be 0, and then 1/0, if that's +infinity, no, that's really bad. Whereas in IEEE, 1/-infinity would be -0, and then 1/-0 would be -infinity, so at least you get it back. And so then you might say, well, then what good are the infinities? Well, the point of the infinities is to use them when you get overflow. So you can overflow to infinity or underflow to underflow to 0, overflow to infinity or -infinity, depending on the sign. Okay, so, but then there's the question, a lot of the machine learning people say that actually they don't even want the numbers to overflow to infinity because they want to use what they call saturation arithmetic, because otherwise they're going to see a lot of infinities. It's with only 8 bits because it's going to overflow a lot. It's interesting because this discussion about how many bits to have, it takes you back also to discussions in the 1940s. In the 1940s, von Neumann, who was the big player then, he didn't want to even have exponent fields. He thought significant fields are enough. The exponent fields can be taken care of by the programmer. Which we see back in the 1940s, computers were super expensive. You had very few bits, and he basically wanted to get the programmer to do everything that they, to sort of not outsource things from the programmer to the computation, which the programmer could actually do. But now we're back to the same kind of discussions with machine learning, because if you look at some of these papers with machine learning, they say, well, in order to avoid overflow, we need to do scaling, we need to scale the numbers properly, which basically means programmer intervention saying, look, before you start doing a calculation, we should scale everything by 2 to the something rather. to try to avoid overflow or underflow. That's really complicated, but it seems, from what I see in the machine learning literature, this is something that people are doing. And if with saturation arithmetic, they won't have to worry about things overflowing to infinity. But then the trouble with saturation arithmetic, what happens is suppose you keep doubling, and you have a very large number and you multiply it by itself, and you'll just get the same number back again because you're already at the largest number. With IEEE, it would go to infinity. And then if you divided that by that large number again, it would still be infinity. So you'd really know. But with this, if you have a very large number and now you start making it smaller again, you'll never really know how big it was. You really lost not just precision, but the scaling. And so again, it seems a little scary. Of course, another big issue is that machine learning is not just being used to detect cats from dogs anymore. I mean, that's the stereotype, right? It's being used for everything. And so there's a lot of risk in doing things that are not sufficiently accurate. So it's very hard to see how all this will play out. And with P3109, I'm sure that we will come up with issuing a report eventually, but whether the industry will have already moved on so far that they won't be interested, I don't know. Or maybe it'll be in step with what the industry is doing. It's hard to tell. Another thing that's happening is that 754, the original floating point standard, they're already gearing up for the next revision because it was 1985 and 2008 late, then 2019 late. So the next one's supposed to come out in 2029, which is, getting scarily close. It's only 5 years away. And this floating point standard is a very complex document, and a lot of things are changing in terms of the details of the hardware and stuff. And so I was also joining discussions. The whole 30109 committee was invited to join discussions about setting up the new 2029 754 working group. That's being led by a guy called Leonard Tsai, who's very on the ball. And that committee will be set up very soon. The working group. I say committee, but the IEEE nomenclature is working group.
Okay.
Working groups are the committees basically that make all these technical recommendations on all sorts of things to the IEEE, approval mechanism, whatever it is, the board or whatever.
I also have one last question, but
Sure.
I think it is a very big one, so feel free to answer as short or as long as you want. I think that we haven't discussed any chips, really. So do you think that any modern architectures are better than others in terms of floating point computations? Or maybe there are some special instructions or special architecture designs? So
yeah, I agree with you. It's a big question. I'm not really the right person to ask because I'm not a hardware expert. But I mean, in general, the Intel chips have been very high quality. They've been very consistent about adopting the standard. The chips that are so Mac. If you look at the Mac, if you look at Macintosh computers, as they used to be called, they used to use Motorola chips, and they switched to Intel chips. Now they have their own chips, the Apple system on a chip. That's the M1, M2, M3. I think they're
M4.
Have they already announced M4? Yeah. So those chips are also very good. I believe that they are very careful about implementing the standard properly. Actually, there's an interesting story that we might talk about, the Pentium bug, but let me come back to that. NVIDIA became a big player in this business through gaming, right? Through GPUs. And the original GPUs were not IEEE compliant. But then they really switched with CUDA. They really started making things IEEE compliant. I think they don't have I believe they do not include the exception flags for the reasons that I kind of alluded to earlier, because it's not so convenient with, multi-threading and stuff and all this parallelism. But in most things, they're IEEE compliant. And Yeah, the Google chips, I'm not so sure because those are doing bfloat 16, but as far as I know, they don't even have gradual underflow. I might be wrong about that. I don't think they've stated whether they have or not. I've talked to somebody at Google who's been super helpful, but there's some things he said he couldn't tell me. And if you'd like to hear the Pentium bug story, that's another.
Yeah, I should there.
Probably know it. Yeah. So as I said, Intel, built all these great chips. Then in 1994, the Pentium was the sort of new thing, I guess then. And Pentium since then has, undergone lots and lots of changes. It's become a brand name of Intel. So there's many, many different kinds of Pentium. But in 1994, your cat is in the picture.
Oh.
Just the tail.
He's also interested in floating points.
Okay, so in 1994, there was a guy called Nicely, Thomas Nicely. I think he was in Virginia. He was a mathematician doing experiments with number theory, and he was doing a lot of computations. He eventually realized that some of them weren't correct. So actually, the most important thing about the standard, I didn't even really tell you. So maybe I should tell you that first. So what the standard really states is that beyond all these, details like infinities and the details of the representation, the most important thing that the standard said is that when you add two floating point numbers, the result should be the correctly rounded value of the true result. That means it's as accurate as possible given the representation. Same thing with multiply, divide, and so on. And it used to be like in the old Cray supercomputers, they wouldn't bother with that. They said, well, we just want to be fast. And if it's not quite right, sometimes it doesn't really matter. Well, that was very much the attitude that, that kind of attitude prompted the IEEE 754 committee in the first place, which said no, that no computations have to be accurate. I should have said this earlier because this is really like a crucial point. But anyway, it's nice to save it for the end, maybe. Well, that means in doubles, 64-bit, that the significance have to be accurate to, so I guess it's 53 bits, the significance or mantissas, because you've got a bunch of bits also for the exponent, 11 bits for the exponent. So they need to be accurate to 53 bits in the significand, including the hidden bit, and which translates in decimal, if you can sort of figure the translation. Log base 10 of 2 to the 53, which is the number. So what is that? It's approximately 16. So in other words, 2 to the 53 is approximately 10 to the 16. That's just a little, mathematical fact. Why do we even use base 10 anyway? That's another interesting thing, right? But it's because of this, right? We all have we have fingers, we have 10 fingers and thumbs, so that's thousands of years old. People use that reckoning in tens idea. I have some history stuff in the book too, if you're interested in more. Anyway, but as I said, binary is the thing to use in computers, and that idea has been accepted really since the 1940s. And but if something is accurate to 53 bits, how many decimal digits is it accurate to? Well, the answer is approximately 16, and that's the reason right there. Okay, so Nicely found that his numbers, which were supposed to be accurate to about 16 digits, they were only accurate to about 4 digits in some very unusual cases. And he thought, well, this is weird. So he contacted Intel, and it turned out Intel actually knew about it, but they weren't telling anyone because they thought nobody would notice. And then it was a huge thing in the media.
But there is also one. There is always one guy.
Exactly, and it was really amazing because if you had tried to convince the public through an advertising campaign that it's really important to have 16 decimal digits, people are just going to yawn, right? Yeah. But as soon as you tell them that they can't have it, then they all of a sudden wake up and say, no, we want that. And that's what Intel said. They said, well, it's okay. Nobody really needs this, and we'll fix your computer. We'll fix the scientists' computers, but the everyday person using a PC, they don't need this. It's really not necessary. And then people were furious. No, we wanted to. And so finally, Intel had to backtrack and had to replace all those Pentium chips, which of course cost them a lot of money. And they had it was very bad press. But in the end, it was actually good for everybody, I think, because now people realize that you really have to be very careful about these things. There are much more attention to proving that hardware implementations are correct, this sort of thing. And there haven't been any repeats about this. And it was so ironic because Intel had done more than any company in history for bringing accurate floating point to the masses, to people in general, non-scientists and non-engineers. And all of a sudden, they were getting bad press. So, but anyway, it came back, and now, for years, there were these laptops saying Intel inside, right? And that's very much appreciated, that the Intel chips are very good. If you look at the top 500, I couldn't find anything more recent than there should be something from even this year and last year, but there's a Wikipedia page for the top 500 PCs processors from August 2022, which is a long time ago.
Based on flops.
Yes, the fastest computers. And of course, these are all massively parallel processors. And in 2022, I think it was like 380 out of 500 of them were Intel, or at least they were x86. No, I think they were almost all x86. I would have to check. And most of them were Intel. The one company I haven't mentioned actually is AMD. I knew there was another one I was forgetting. AMD pretty much makes all the same chips as Intel does, because they struck a deal with Intel way back in the 80s when IBM adopted Intel. This is another super ironic story, right? IBM adopted Intel to make their PC because they didn't think that, to make the chip for their PC. In those days, they didn't think that the laptops were going to be a serious business. They had their big mainframe business. We're IBM, big company. Intel is just this little startup thing. Of course, now Intel is a far bigger company. And also, of course, another small player back then was Bill Gates and Microsoft, and they got the deal with Intel, and then, of course, Microsoft became much bigger than IBM too. So these things are all very ironic, right? Well, the reason that AMD got to make the same designs, same Intel designs, was that IBM said, look, we're not going to be just stuck with this little company, Intel. What if Intel goes bankrupt? We need a backup. So they insisted on a second company. This is all documented in a book called, I think it's called the computer, I forget. I could look it up. It'll be in the second edition.
Okay.
Not a book by me. I mean, the book that describes these IBM decisions is something published. Anyhow, they insisted on another company being able to sell these too. Also, AMD was kind of secondary to Intel for a long time, but then Intel really stumbled in the early 2000s with their IA64 design, or no, IA32, I guess it was. Was it the Titanium anyway? I think it's IA32. And what happened was it didn't really get adopted much widely, and AMD made something that they called, I think, X64 or something like this. I mean, X86, I guess. Yeah, because all these Intel chips, they all became known as X86. The original floating point was X87, 8087, and then the 87 was absorbed into the X86, and Pentium is part of the X86 sequence. And then AMD was making these X86, and they went to the 64-bit processor, which refers to not to the floating point, but to the way the memory is organized with 64 bits. And then so the AMD X86 design got adopted widely, and even Intel eventually switched to that. So that's kind of a long-winded answer to your question, I think.
Yeah, but as always, I learned a lot. So thanks a lot. I think that we should wrap it up because it's almost an hour, or maybe just even more than an hour right now.
Might be, yeah, it is.
Yeah. Thanks a lot. I learned a lot, really.
Well, thank you very much.
I had a great laugh, and I think that our audience will enjoy it as much as I
Oh,
did.
that's so great. I'm so delighted to hear it. And the second edition will be out there before too long.
Yeah, I will put any links that you send me in the description. And thanks a lot for answering all my questions, going deep into the history and into the technical parts. It's really awesome.
It was really a pleasure.
Что ж, я надеюсь, что вам понравилось интервью, потому что я планирую делать довольно много разных интересных выпусков с гостями, которые лучше разбираются, чем я в определенных вопросах. И надеюсь, что эти гости с удовольствием расскажут о большом количестве разных сложных технических аспектов, которые так или иначе связаны с питоном. Если вам понравилось это интервью, вы можете сделать несколько вещей. Во-первых, подписаться на мой GitHub. Не забываем, что именно там я размещаю все материалы, которые делаю в рамках этого курса, большое количество интересных ссылок, большое количество практических заданий, а также интересных утилит, книг и прочее, прочее. Также можно подписаться на Boosty и поддержать проект, если вы считаете, что полезная информация, которую я несу в мир, того достойна, и присоединиться к нашему Discord-сообществу. Там много разных объявлений, там можно получать уведомления о том, что вышли новые выпуски, и оставаться на связи. Вот. Надеюсь, что вам понравилось. Спасибо, пока.